Okay, by my watch, it's just about time to go, so let's get started. Talk today is going to be about milkymist, the architecture for the open hardware world, and our guest today is Sebastian Bordeduc. Please give him an excellent, warm welcome.
Everybody, thank you for coming. So, as you said, what I'll be presenting today is a project on which I've been working for approximately 2.5 years. I will give today a short introduction on how it all started, because it initially began as basically an embedded video jockey box, and it turned out to be a complete system-on-chip design. I mean, I really wanted to open everything. Then I will give a short introduction about what are the planned features of the initial design, what the VGA box was supposed to do. And then I will give a rough outline of the features of the system on chip that I have designed, or which I'm currently designing. Then I will move on to give some points, some very technical points about some aspects of the design that are quite challenging, because designing with video involves high-speed logic, computer architecture, many different domains. And I will just outline a few common problems that you can encounter if you want to build your own high-performance system on chip. And finally, I will give a short presentation of the software which you can run on it, for example, Linux or graphical user interface toolkit. And then I will finish with how you can develop yourself your own chip on an FPGA platform. So let's start with the introduction. So it started, as I said, as a device for video performance artists called VJs. It was inspired by the popular milkdrop program for PCs. So milkdrop is a plugin for Winamp, which displays in real time some visual effects coming from the music, which are rendered with graphics acceleration on your video card. And I wanted to integrate many interfaces because I began VJ like, I don't know, maybe 5 years ago or something. And I have built my own VJ software, which was never released because the code is awfully dirty. But it was based on milkdrop, and I added many things. I wanted to make my performances interactive. So I did things like DMX control, MIDI control, or even control with the touchscreen of a PDA. You could take your PDA and draw on the screen, and it was appearing in real time on the video projection screen. This turned out to be quite popular in concerts. And I didn't want to carry around my tower computer with with big graphic cards, all the interfaces, USB switches. It turned out to be messy. And I thought it would be cool to have some very small embedded devices which would integrate all these things. And that's how I came up with the idea of building this embedded VG platform. So I wanted something at the frontier, somewhat between big computers with software to render visual effects, which I was using before, and a small handy microcontroller board, a bit like Arduino that most people know. So I will just give some examples of pictures you can get out from milkdrop. This doesn't really do justice to milkdrop because these are still pictures. If you see them moving in real time with music and some interactivity with MIDI, DMX, video, or anything, it gets much more impressive. So that's another type of visual effects you can get from milkdrop. So, as I said, I wanted to make something which is really open hardware. I will take, for example, the Arduino, which is often touted as being open hardware. Well, basically, Arduino is just an IVR microchip, power supply, and connectors. And in this design, the IVR chip does all the magic. Everything that the Arduino does is basically done by IVR. And the IVR is a black box. I mean, it's a chip in every sense. You have a plastic package, and you don't really know what's inside. So basically, Arduino isn't really open hardware, because on the other hand, you can describe all the logic which is inside the chip, and you can open source it. And this Atmel, they will never do that, because the source code which is used at Atmel, in the Atmel company to build the IVR is trade secret, proprietary, whatever, or patented, even patented sometimes, and they will never open source it. But I wanted to make this VGA project a really open hardware thing, and that's why I went on to design my own chip. And this has also another technical advantage. This has also technical advantages, because if I wanted to do it the traditional way by using general purpose chips, I would need a very powerful and specific chip, for example, Texas Instruments OMAP, and this chip is well, it's proprietary, as I said, but it's even more proprietary than AVR because you have to sign sometimes NDA, you have binary only drivers sometimes, so it's really not a good solution for open hardware. And also, the advantage of making my own chip is that I can integrate all the interfaces. For example, I spoke of video inputs, I spoke of MIDI, of DMX. If I wanted to interface all this using a Texas Instruments OMAP chip, this would get awful because I would need many other chips on the PCB to take care of all these interfaces. So there are already some other projects which has went. Yeah, sorry, it doesn't work well. Yeah, thanks. Better. Okay. Yeah, so there are other open hardware projects which has went the same way. There is, for example, a grlib, which is developed by Auroflex Geisler. They are most well known for their Leon 3 processor, which is compatible with the Spark. It has been used by the European Space Station, for example. There is OpenSpark. Sun Microsystem is quite open source friendly, and they have released the source code for their Spark processor in Verilog. Unfortunately, it's very hard to use OpenSpark yourself because you need very big FPGAs. OpenSpark is a very complex design, which has many optimizations, and sometimes when you are doing FPGA, it's better to have a more simpler processor, which could run faster, because when you implement all the features which are in OpenSpark in an FPGA, you get very complex logic function with many levels, and the clock frequency goes very low, and it also eats up many FPGA resources. So OpenSpark is not very accessible to hobbyists. There is OpenGraphics. OpenGraphics is very ambitious. They want to build a graphics card for computers, which means it would compete with the high-end graphics card from NVIDIA and all the like. So it's very difficult to do. And there is it's not really a fork, but it's close to Project VGA. It's also a graphics card, but it's a lot less ambitious than OpenGraphics because they don't want to make a complete graphics pipeline. They just basically want a frame buffer and VGA compatibility. Project VGA is really accessible. And there are other projects, for example, OpenRISC from OpenCores. So what I wanted to do is go the same way and build my own system-on-chip design for the milkymist project. So I will just give now a short introduction of what the system-on-chip should do. So that's basically implementing milkdrop, because my former VG program was also based on the milkdrop system. So milkdrop is working with an iterative rendering paradigm. So basically it takes the current image. You can start from black, for example, and you will distort it. So you have a set of equations that you can parameterize, and this will give a distortion to the image. You can zoom, you can rotate, you can scale, you can warp in any way you can. And once you have done it, you draw some waves, which are made from the music, and you draw some shapes as well, like polygons or anything, gradients. All this is parameterized by the music, or in my case, other interfaces such as DMX. For example, you could well imagine that the zoom is controlled by the lightning table with a slider on it. And once you have that, you display the result, and then you repeat the process over again. So the image gets distorted, and the wave gets drawn every time. And this gives the effect that I have shown before. Sometimes you can play with it to draw some fractal images, for example, or anything. Well, that's a bit simplified process, but the big picture is this, about the functioning of milkdrop. So as I said, the distortion and the wave drawing are controlled by fully customizable equations, and this is called milkdrop calls a preset. It's similar a bit to a patch in pure data. And by changing these equations, you have some parameters, for example, extracted from the sound, for example, the bass level, or the treble level, or the beat, or anything. You have these parameters in the equation, and you can combine them with a large panel of mathematical functions. So you write some equations, and you put them into milkdrop, and it gets some nice visuals. And as I said, I want to add some DMX and MIDI interface, also OSC from Ethernet, and interaction with video. You could, as well, for example, imagine a computer vision system reacting to video, or even some instead of taking a blank picture, you could take the frame from the video, film the audience, the artist, or anything. So the challenges involved with designing such a system are first the need for a CPU, because Milkrop overall is a very complex system, and if I were to implement everything in hardware without any software, it would get horribly complicated and not even efficient, because I would need many big state machines, which would fill up my entire FPGA and which would be awful to program. So it definitely needs a CPU for taking care of the software-friendly tasks, like the GUI interface, field file system, protocols, all the housekeeping of running the graphical pipeline. And it also brings out some flexibility, ease of reprogramming, and also you can easily patch software bugs without recompiling the whole FPGA design. The other challenge is even though the FPGAs are getting cheaper, you still have to be very careful because they are not so cheap. So you have to make a very careful design and strike a good balance between hardware and software to get the best compromise between speed, size, and cost. Basically, software is cheap and slow, and hardware is expensive and fast. So you have to balance and choose what to put in software and what to put in hardware. You have a big problem that I had, it took me 1 year to solve, are the memory problems. Because you need a lot of memory bandwidth to take care of the video, and you also need a lot of memory to store the frame buffer, the textures, and everything. And the only technology which is capable of doing it is DRAM. And DRAM is very hard to take care of, especially at high bandwidth. And finally, you have compute-intensive operations. For example, distorting the image and evaluating the equations need a lot of processing power that you cannot really do on the CPU. So the architecture that I have chosen is a system on programmable chip. So a microcontroller, a bit like AVR, but a bit more powerful, is implemented in the FPGA fabric. So microcontroller is a CPU plus some additional peripherals, like UART, like GPIO, video frame buffer, all this. Then you write software and compile it with GCC, for example. And the processor that I'm using is Lattice Micro 32, is supported by GCC. Even the patch is included in the newest GCC. So you compile it with GCC, you load it into the board, and then the microprocessor made from the FPGA fabric will execute your software. And from your software, you can drive an acceleration unit and special peripherals that you add into the FPGA fabric and drive them with the software. So now, as I said, I will start with studying some cases. And first, as I said, the memory problem is a very tough one. So I will a bit explain how you could solve it. So the application requires memory to be big. You need a lot of memory for textures, frame buffer, all the like. Fast and cheap, because I want the device to be accessible to most people. And the required memory size prohibits the use of SRAM, because a very easy memory technology to use is SRAM, stands for static RAM. But if you need a big memory size, SRAM gets extremely expensive. For example, if you buy a 4 megabyte chip of SRAM, it will cost like 100 euro or something, so that's out of the question. So I have to use DRAM, like in computers, for example. You know, SDRAM, DDR SDRAM, DDR2 SDRAM. This is the type of memory that I have to use because of the cost constraint. And this memory is very hard to drive. So first, I will just see how much memory I need, how I can do it. So I will draw the table of the memory bandwidth usage and memory capacity usage. So first, what I need in my system is a VGA frame buffer running at a nice resolution. And if you do the math, this resolution requires nearly 1 gigabit of memory bandwidth, approximately 2 megabytes of size. Distorting the image is also a big memory bandwidth consumer. You need 700 megabytes per second. Then, as I said, I needed also video inputs. They don't use so much bandwidth because NTSC or PAL video is not so high resolution and not so high frame rate. So it doesn't eat up so much bandwidth. And finally, for software, for example, the graphical user interface, for the UART, for whatever, the sound IO, for example, you need roughly 215 megabits per second. So if you sum up all this, you see that the memory chip must have a sustained bandwidth of 2.2 gigabits per second. So between the FPGA or the custom chip, if you want to make one, you will have a continuous flow of data, which amounts to 2.2 gigabits per second, and the total capacity of the memory is approximately 22 megabytes. That's only the basic system that you will need. So let's see what the memory market has to offer. If you take, for example, the DDR SDRAM, which is commonly found in computers, most laptops use it. Now they are more using DDR2, but it's very similar. If you run it at 100 megahertz, it can give a peak bandwidth of 3 gigabits, and it can have a 32 megabytes capacity, and it costs a few dollars. As you can, when you buy your memory for your computer, you can see that it's very cheap, especially if you need only 22 megabytes. Today's chip take hundreds of megabytes and are not expensive. So, well, it looks like still manageable. But there is one thing that is a big problem. It's 3 gigabytes is a peak bandwidth. This is a big problem because, as you will see, the performance of CSDRAM depends a lot on the cleverness of the controller. For example, I will just give one of the examples, which is easy to understand, to explain how you can get the most bandwidth out of a memory chip. For example, if you have a very simple SDRAM controller, you issue a read first here, and then you wait for the data, then you continue your execution, and you need another word to be taken, so you need another read command, and then the data has to come a few clock cycles later. And, well, you can see it takes a lot of time if you wait for the data before issuing the next command. If you have a more intelligent SDRAM controller, you can issue a read command every cycle, and then the memory will give the data with a bit of latency a few cycles later. And you can see that if you optimize the SDRAM controller, the memory access time will really shrink, and you can really use 100% of the bandwidth, because if you keep the figures that I gave, which is 3 gigabytes for a DDR200 chip, is when every slot is taken here. But to take every slot, you need to issue also a read command at every slot. And so you need to predict perfectly the address sequence that you put into the SDRAM. And on top of that, you have other problems like memory refresh, or sometimes you have to change rows in the DRAM array. But well, these are more technical points that I'm not going to cover today. I will just explain this. So if you want to predict the address sequence, it's hard, because typically if you have, for example, a for loop, the CPU must be able to do some kind of speculative execution, or, to things that the program, if you have, for example, a for loop, if you want to copy 2 buffers, for example, if you load one word and then store it in the next, you have to reorder the instruction in order to be able to continue execution, even if the memory has not given you the data. But you need to continue execution to compute the next address, and that's pretty hard to do in software. But what you can do, which is a much simpler solution, which doesn't need an out-of-order CPU, is do something which is called bursting. Every time you do a memory transfer, you get the first read command, and then you read the consecutive words. And in milkymist, I am using a burst of 4 words. So every time I request any word from the memory, the controller automatically requests the next 3 words. And I will then discuss how it could work, because it may seem a bit strange to do that, because you're not even sure if you're reading the next word or not. But I will then discuss that. So let's see if it's a good idea. Well, is it good for the VGA frame buffer, for example? Well, the VGA frame buffer, as you have seen from the table before, is a big bandwidth consumer. So let's see how we can do that with it. So every time it gets a burst of 4 consecutive chunks from the memory, these chunks they also represent consecutive pixels in the screen scan order. So when you get the burst of 4, you just put them into the FIFO, and then you can slice it every time the screen needs a pixel, and you achieve 100% bandwidth utilization. So it's perfect. For the PAL and TSC video inputs, it's exactly the same problem. Only you're not reading, you're writing. You're just getting data from the video input. You put it into a buffer, and when the buffer is full, which means it contains 4 memory words, you just put them into the memory controller in a burst, and you also achieve 100% utilization. Is it good for distorting the image? Well, yes, it's good. I will explain it later. So it seems a bit strange, because you can see the image needs to read pixel in if you are distorting an image, you need to read pixels in strange orders, but you have a way around it, and I will explain how. For software, you can use caches, and caches works with the principle of temporal and partial locality, which means that when you are accessing a world of data, you are likely to access in the next milliseconds the words which are nearby. So you can put the complete burst into SRAM, which is on chip, and every time the software requires a word, you search this cache, and if it's in the cache, you can get it in one cycle. Otherwise, you have to fetch from the main memory. And in the cache, you store always the complete burst every time you get them from the memory controller. And using this burst system, it really simplifies a lot the SGM controller design, the signaling of the memory bus, arbitration of the bus, and also cache controllers. It's really stupid. I mean, you just have to have a counter inside your memory controller, and you request all addresses, and it turns out to work pretty well. You don't have to do any kind of speculative execution or anything complex. So I will explain now how you can distort an image with a good performance. So first, what I mean with distortion. Distortion is basically doing this effect, as you can see in the picture. You take a square image and you can just shrink it, or you can zoom it, you can do whatever you want with it. So more precisely, what I'm doing is what is called texture mapping when you are doing OpenGL. So basically, the milk preset equations, they define a mapping that I call F, which transform a point which x and y coordinates into another point which has another x and y coordinates. And this mapping means that the point at x and y coordinates in the source image should be at capital X and capital Y in the destination image. For example, if you want to zoom by a factor of 2, you can use this function, which multiplies each coordinate by 2. So if you have this first pixel, it will be at 0, 0. The next one will be at 2, 2, etc. So it just expands the pixel. But the problem you have with it is that how to fill the holes, because if you scan the source image and apply the function every time, you will, if you take this function, for example, you will only fill 1 pixel out of 2 in the destination picture, and this cannot work. So what I'm doing and what graphics cards do is called the tessellation. So you are covering the image with squares, and then you distort these squares, and you have a primitive for distorting squares or triangles in the hardware. So what I'm using is a triangle strip. So I tessellate the source image with triangles like this. Then I apply the mapping at each cross point in the grid here. And then some unit will draw each triangle in the destination image here. So that's basically interpolation, linear interpolation to fill the blanks in the image. So now this sounds quite easy. I mean, you can just do it with some software. But the problem here is performance. If you want to achieve 30 frames per second at XVGA resolution, the texture mapping unit, it must process 24 million pixels per second. Which means that if your system on chip is running with a 100 megahertz clock, you have only 4 clock cycles to process 1 pixel. So if you are doing a naive implementation, which could be software, for each pixel, you need 100 cycles of mathematical operation. If you are doing stupid memory access, you need 12 cycles to read your pixel and 12 cycles to write one. So in total, you have 124 cycles if you do it in the software. Well, that's not good. You need 4 cycles, and if you do it in software, you have 124. So what can you do for this big speedup that you need? First, you can improve the algorithm. So math that I gave was done in a stupid way with a lot of multiply and divides, which is very slow. You can do implementation with the Bresenham linear interpolation algorithm, which is much faster. You can also do simultaneous SIMD parallelism, which means that the same operation and independent data can be done in parallel. For example, computing X and Y in the source image are completely independent operations. So you can have 2 similar units and feed them the data, and they can process in parallel. You can also pipeline. You can also use pipelining. Pipelining is basically the equivalent of chain work. You have a chain of small hardware units which are very fast at performing a very simple operation, and they work in a chain. For example, in the milkymist texture mapping unit, I have made 14 pipeline stages. The first stage will fetch the vertex data from the bus, I mean the coordinates for the distortion, and it will keep fetching and put them down the pipeline. The other one will do, for example, computing the deltas between the pixels. So it doesn't go very fast, it's only an operation. So another pipeline will do the divisions required for the Bresenham algorithm. Then another stage will do the actual approximation. Another one will scan the triangles. Another one will fetch the source pixel, and it's like chain work. And this gets very fast. I have only 14 pipeline stages. This will go as I add more features to the graphical pipeline. And if you take a commercial GPU, on some architecture you can have hundreds of pipeline stages. Finally, as I said, you need smart memory access, because in my previous computation, you needed 24 cycles in total. So memory is already a problem, because you need to process the complete thing in 4 cycles, and memory is already taking 24. That's bad. So what the techniques I'm using is using a cache and a write buffer. I will focus now on the memory read problem. I will not explain the other things. So for reading the memory, currently it takes 12 cycles and you have at most 4. So what I will be doing is using the burst memory and putting them into a cache. So a cache is a SRAM chip inside the FPGA, which can store some number of limited number of bursts, because the cache has a limited capacity. If you put too big a cache, you need a lot of memory. And as I said, SRAM is extremely expensive, especially if it's on chip. So you have to limit the cache size to a few kilobytes. So it limits the total number of bursts that you could take. So now, the problem is, when you have a burst here, this pixel was needed. So you're sure that this read was absolutely needed. But the problem is, will you be able to also use this other data that you get from the burst? So that's what I'm going to explain on a simple example, the rotation of a triangle. So you have the original triangle that you need to rotate here, and when it gets rotated, it ends up with this triangle, and the texture mapping unit in milkymist is filling these triangles with scan lines, which means that it will draw all these pixels in this row, then all this one in this row, etc., etc. So, and when you see what happens from the original triangle, which generates the memory reads, you can see that it tries to fetch data from here, in this order. So let's see what happens when you draw this scan line and then this one. So you draw this one, and you fetch these pixels. These pixels are not in the cache, if you assume the cache is empty at the beginning. So all these pixels will generate cache misses here, and cache misses will generate memory read bursts, and the memory read bursts are linear, and the frame buffer is also in linear scan order. So the pixel which gets fetched from the burst are these ones. And so this scan line gets drawn, and all these pixels here end up in the cache. And then, when the texture mapping unit draws the second scan line, it draws it like this, and these pixels need to be read, but as I said, they are now in the cache. So this will generate cache hits. So these cache misses will take like 12 cycles to get, these pixels will take 12 cycles to be read from the memory, but these ones have been put in the cache because of the previous reads, and they will only take 1 cycle. So it looks like it can work. So I have done some simulations of the design. I have completed the design of the texture mapping unit with including a cache, and I have done some simulations on real cases. So I have taken some sample maps from MIGDrop, and I have put them in the simulation. I have run the simulation for a few hours, and it ends up with this graph. So here you have the cache size in bytes. Here it's 10 kilobytes, 20 kilobytes, etc. And here is the hit rate. So the hit rate is the percentage of pixels which are served by the cache. So when you have a cache hit, it takes 1 cycle, otherwise it takes like 12. And as you can see, even with a small cache here, you already have a very good hit rate. And then if you keep increasing the cache size, it doesn't improve much, but it uses a lot of memory. So a good compromise would be to use a 4 kilobyte cache. It's only 4 kilobytes, it costs peanuts. It really fits in the FPGA. You have 94% of the requests get served from the cache. And if you compute the average memory access times, it's only 1.4 cycles. So the problem is solved. Now you have reduced the memory access time from 12 cycles to 1.4. That's perfect. So another study that I needed was evaluating the mail drop equations. I'm also using some tricks here that I'm not going to cover. Basically, I needed a floating point hardware coprocessor, and the main CPU is compiling code on the fly for this coprocessor in order to further reduce the hardware usage in the FPGA. I'm not going to explain a lot into the details, but basically you have several floating point pipelines and a very low-level instruction set which says put that into the pipeline and fetch that from the pipeline. And the compiler needs then to schedule all the pipeline by itself. And by doing that, first you remove the need for a scheduler inside the hardware because all the scheduling is done statically in the instructions. And also the compiler is able to extract a lot of parallelism from the computation which need to be done. And this gets a very fast system. On real cases, with an FPGA running at 100 megahertz, it does 75 billion floating point operations per second, and uses, on this FPGA, which is Vertex 425, it takes approximately like 20% of the FPGA surface. So it's not too bad. Now I will explain a little bit. I will just present a little bit some software that you could run on the CPU. There has been a port of Linux, which is made by Takeshi Matsuya from Keio University, mostly. That was a nice contribution. And now the board is now supporting Linux. It's only the no MMU port of Linux, because so far the CPU doesn't have a memory management unit. That could be a very nice contribution to design an MMU for Mico32. You also have the GNODE-FX GUI toolkit. It's a very embedded toolkit. It doesn't require the C library. It has also been ported on the milkymist system, so you have windowing, mouse, all you want in order to make a very friendly system in the end. So now let's cover some details about how you could develop FPGAs yourself. First, the development board. Most of the development were done with the Xilinx ML401 board, which is pretty feature-rich. I have bought one here. So this board has a VGA output. It has some serial port for debugging. It has some USB, a CF card reader, LCD screen, DDR SDRAM, audio. I think that's all, basically. Oh, it has Ethernet as well, gigabit Ethernet. And it has a Vertex 4 FPGA. It's not a very big FPGA, but you can still do some nice stuff with it. And it's affordable. Now it's obsolete, unfortunately. But when it was released, it costed $500 only. So it's pretty okay for such a big board. For the software, first you need a lot of simulation, Verilog simulation. The complete system was written in Verilog HDL. And you need definitely simulations on this system. First, to explore the cache size that I have shown, you needed simulations. Because you will not increase the cache size as you want in the hardware. And also for debugging, because debugging such a complex system is very complicated. And if you are not able to see what's happening inside the design, you can just forget about debugging anything, because you will just put into the FPGA, it will not work. And then, you just cannot guess what's going on in the design if you don't have a simulator and if you're not able to pick inside your design. And even sometimes in the most aggressive bugs, post-process the result of the simulation to figure out where the bug is with some script, Perl, or anything. So the good news for you is that there are 3 simulators. There are Icarus Verilog that I used a lot, GPLC there, and there is also Verilator. Verilator is very innovative because it's actually compiling Verilog code for your CPU. So it gets you a very fast simulator. The problem is that it has a lot of bugs. So I didn't use this one much because it took me too much time to figure out if the bug was in my design or in the simulator. But Icarus Verilog and GPLC there are pretty reliable. They're very light. They can run without a hitch on small laptops like this one. So you can really debug your Verilog code wherever you are. Try to do the same with the big simulators, which are very heavy. They take gigabytes of hard disk. And they have also this very inconvenient FlexNet license system, which requires you to connect to a VPN and then to a license server. And fortunately, I didn't need any of the simulators. I did everything with the free ones, which is good. For the logic synthesis, I have worked with ISE Webpack from Xilinx. It's proprietary software. There is no free FPGA software available now, unfortunately. I hope someone will develop it someday. But there is a Linux version, and it's pretty good quality if you use it in command line. Graphical user interface has some very inconvenient bugs sometimes. But in command line, it's okay. It's heavy, it uses a lot of disk space, it's slow, but in the end, it gets the job done. For the software development, as I said, the CPU is supported by the GCC compiler. You can compile C on even C++. I haven't tried C++, but yeah, I'm not sure if it works. And the patch for supporting Lattice Pico 32 has been put into the upcoming GCC 4.5, which means that you will not need a patch anymore for compiling software for milkymist. And for debugging, I have made some nice terminal programs that can download the software from the serial port, which speeds up debugging software development a lot. So, in conclusion, I would say that the wide availability of FPGAs open new fields for DIY hackers, hobbyists. One of the fields, high-speed embedded computing and its applications. I have presented a couple of high-performance design techniques. I didn't invent them. They are everywhere in the computer industry, but you seldom hear from them because most of the time they are covered by patents, industrial secrets, or everything. So you never really heard of them. And the biggest problem also was that if you wanted to build a chip, it's very expensive, and FPGAs were also expensive until recently, so you could not really test and experiment with high-speed logic. So, well, you could not really learn from it. But now if you take a FPGA board like this, you can really experiment a lot and figure out all these things means in practice. So thanks for your attention. If you want some more information, you can check out the website. You can get the documented source code, which has GPLv3 license. You can get binary kits, which has, precompiled stuff for FPGA boards. So if you have a supported FPGA board like this one, you can just flash into it, and you will get it running in a few seconds or minutes. You have mailing lists if you want to stay tuned. You can edit the wiki. There is a list of contributions if you want to help a little bit with projects. You can find project news on the blog as well. And of course, the slides are also online. Now, before I switch to the questions, I will just make a short demonstration of the system. So I just connect this FPGA connector to the board. So I will start UC Linux. I hope it works. Okay. Yeah, that's the splash screen. So now it's reading the CF card. It's loading the kernel and the initial RAM disk. And it should boot in a few seconds. Yeah, good. Now it's loading the RAM disk. There you go. Now you have free software running on free hardware. You can check out the uname. LM32 processor. CPU info is also nice. Basically everything is working. You have virtual consoles as well. If you want to do some multitasking.
Does it have Ethernet?
What?
Ethernet?
Not yet. Coming. Now I have a lot of problems with linking things with UC Lab C, so I cannot have networking running. CPU usage should go up. Yeah, 99%. that's basically a Linux. I have made some video effect demonstration program. I'm not sure if you will see anything on this video projector because it's pretty dark usually, but I'm starting to boot it anyway, just to show a proof of concept milk drop-like application running on the system. Yep, that's running. Now I will load the milk drop preset. Yeah, it's working now, but yes, it's very dark. I mean, that's a proof of concept system and it's not so good. But if you want to check out more, you can go to the Paris hackerspace booth at the top, and you will be able to check it out on the screen, play with it, and it should look better. Do you have any questions?
Well, I thought the demo was pretty cool. No, that's not yet. Well, I thought I had a mic. The one over there by the camera is apparently working better. And Sebastian, could you please repeat the question for the camera?
Sure, okay.
Great, thanks. Oh, this one is working. Come on, come on.
No questions?